Good afternoon, everyone. Welcome to Nature Live Online. I'm Alison, your host for today. Now, if this is your first time watching a Nature Live, these events give you a chance to meet some of the scientific staff that work behind the scenes at the Natural History Museum in London. You can find out all about them, what they do behind the scenes, and see some more of our collections. While we can't physically be at the museum right now, what we're doing instead is bringing our science and our scientists direct to you at home. And I am really pleased today to be joined by one of our curators, Katie Collins, and we're going to be finding out all about bivalves and why they are so brilliant. Now, remember, we are live, so if you do have any questions, please do post them in the comments. We love to hear from our viewers. Don't be shy. Pop your questions in the chat. We'll do our best to answer as many of those as we can. But let's meet our speaker for today. Katie, are you there?
Hi.
Hey, Katie, thank you so much for joining us today.
Yeah, it's nice to be here. How are you?
I am very well. I'm excited for this talk. I'm a bivalve convert.
Excellent. That's what I like to hear.
Now, Katie, let's find out first of all what you do at the museum.
So I'm the curator of benthic mollusks, which means I look after all the mollusk fossils that aren't ammonites. So the snails and the clams and the tusk shells and the rostroconchs and a couple of other weird things. And mostly, as you can see from these pictures, it means I put things in drawers and I take them out of drawers and I make them accessible to people who need them for research. And sometimes I get to go and look for new ones out in the wilds, which is fun.
Absolutely, we're missing being in the collections, but also out on field work. But hopefully soon this will all pass and go back to normal.
Fingers crossed.
Yeah. Now we're going to focus today on the bivalves, but let's start with some basics. What exactly are bivalves, and where do they sit in the tree of life?
So bivalves are mollusks, which means they're part of the big group that includes squid and octopus and snails and a bunch of other things. And they're bivalves because they have two shells, two valves like that. And in the tree of life, they sit probably within the mollusks. They sit with the tusk shells and the gastropods. But within the tree of life, they're closest to annelids, so earthworms and brachiopods, which you might have heard about from my colleague Zoe, and the bryozoa. And then those are sister to things with legs, like arthropods. And then those two groups together are sister to things with backbones, like us.
And the clue is in the name, bivalves. You mentioned they have two shells, but what's inside?
What's inside is mostly gills. They don't have a head, which is something that startles people. They don't have a head. They are mostly gills and a muscular foot that they use for digging with, but also jumping and exciting things like that. And what you can see here is the shell from the outside with two valves. I've drawn a line down the middle so you can see where they split. And then on the other side is a mold from inside. So sediment has got into this fossil bivalve, and we've lost the shell, but we have the mold of what was inside. And you can see what is imprinted on the inside of the shell is the muscle attachments, those two circles, and then the line where the soft body actually attaches itself to the shell called the palleal line.
Bivalves jump?
They do. Sorry, I just revealed this amazing information. They do. Some of them are very active jumpers. There's a famous story about a guy called Starchbury, who was a shell collector who went to collect a very, very rare and exciting shell in Australia, and he claimed that it jumped out of the boat after he dredged it back to freedom.
Fantastic. And how diverse are bivalves?
They're very diverse. So from this sort of basic body plan of just sort of a headless lump of gills inside a shell, they have become ginormous. So giant clams, the middle one there with the zigzaggy, we call the commissure, the place where the two valves meet, the mouth, they get to be hundreds of kilos and over a meter in length, and they're massive. And small bivalves, they can be down to under a millimeter in length, or some of them grow spines, and some of them photosynthesize, and some of them dig deep tunnels, and some of them look like watering cans, like the beautiful clavigellid there, which the shell is actually very relict, and it's embedded in that long tube, and it grows this huge tube that it lives in. And the bivalve part is very small.
Yeah, I was amazed by that one, the one that we can see there, bottom right, that watering can.
Yeah.
That's a bivalve.
That's a bivalve. That's that's one of the weirder bivalve forms, and it's from this group of bivalves called the Anomalodesmata, so anomalous. They're weird animals, and most of the really bizarre bivalves live in that group. That's where the carnivorous ones are, and yeah, strange little creatures.
And whereabouts do we find them? What sorts of environments?
We find bivalves anywhere you get water, pretty much. So they haven't made it onto dry land like snails have, because it's difficult to sort of filter feed in the way that they do on dry land. You do need water for that to happen. But they live in lakes and they live in rivers and they live in the deep sea and the shallow sea and everywhere there is sea. They live on black smokers that are pumping boiling hot metal laden water out of the under the crust, and they live under the ice shelf in Antarctica, where there's like a foot of space between ground and the sea ice, and then you find beds of these beautiful maroon scallops that live there.
Yeah, they are absolutely stunning. And you mentioned filter feeding. Is that how all bivalves eat?
Almost all. It's definitely the dominant way that they eat. So like these guys here have the little wormy thing. It's called a siphon, and that's how lots of them suck in water and then put it back out again, and they filter what comes through. Some of them are deposit feeders, so they're more like little vacuum cleaners of the sea, and their soft parts will sort of feel around and find and take in debris. Or they can also do that from within the seafloor. They still sift around in the sediment that they're burrowing in. Some of them are carnivorous. They eat copepods, so little greeblies that live on the seafloor. And some of them are chemosymbiotes, so they have bacteria in their tissues that can eat nasty sulfurous mud. And some of them are photosymbiotic, so they have, like these guys, yeah, so they have symbionts that can take sunlight and turn it into food. So you've got two kinds here. There's corculum at the top and then fragum at the bottom. These are two different kinds of bivalves that supplement filter feeding with photosymbiosis. And their big famous relative is the giant clam, which we all know is beautiful and photosymbiotic itself. Yeah,
Absolutely. So is that a little bit is that in the same way that corals, for example, have photosymbiotic?
So yeah, quite similar. They have a little symbiont. In the case of bivalves, it's a thing called symbiodinium. I don't know if that's the same one in corals. Sorry.
Okay.
But similar kind of a deal. And
Yeah.
they live on the seafloor in shallow, warm water where the light can get to them. That's very important. If it's too deep, they can't get light, and then their symbionts don't work. Yeah.
And the giant clam is a fantastic example. We're all sort of familiar with oysters, with mussels, but there are some surprising, some unusual types of bivalve, aren't there? The giant clam being one example.
So the giant clam is kind of one extreme of this giant photosymbiotic bivalve that lives on reefs. You also get bivalves that are, as I said, there are carnivorous ones, there are swimming ones. So here's a picture of a tridacna on a reef surrounded by corals.
It's incredible.
And then there's some in our collection on a giant shelf that's about the height of my head. So we're never getting those out again.
No, they're staying there.
They're very heavy. I cannot move them. But also we have bivalves that live in the deep ocean and never see the sunlight and have hardly any calcium to make shells out of. So they make these beautiful thin, paper thin, glassy shells, and they're carnivores because that's the only thing they can really eat down there. They do all kinds of things.
One of my favorites that I never knew about before we kind of researched this talk is the disco clam. Tell us about this one.
I love the disco clam. So most of the things we know about the disco clam, we know because of the work of a grad student at Berkeley, Lindsay Doherty, who's done some amazing work, and I highly encourage you to Google this. The disco clam is a little lemid bivalve, so a relative of scallops, and they jump and they swim and they flash like a mirror ball. They actually use little biological mirrors in their tissue to reflect light and flash, either to sort of warn off predators or to lure prey. Lots of things in the ocean are attracted to flashy, shiny things. It looks like motion, I guess. So yeah, these guys have managed to find a very exciting way to live for something without a head or a brain or, legs. anything else.
Definitely.
Yeah.
They are beautiful. I would urge people to look them up because there's some great videos on
Mm,
YouTube of these. They are beautiful and yeah, so unusual.
they're
And
just gorgeous.
another great group that I didn't realise were actually bivalves are shipworms. So they drill, don't they?
They do. So shipworms are one of my favorite groups of bivalves. They do some really cool stuff. So what you've got here is a picture of a dried shipworm. So normally they're sort of straight and squidgy, but this one has kind of done this in preservation and tied itself into a little knot. And then on the other side, you've got a picture of wood where that shows the holes that they bore in. So on the little ring-shaped picture of the actual bivalve, that white part is the two valves of its shell that have been modified into basically a drill bit, like a rasp. If you look at them when they sit together, they have just two big like blade faces to them, and they just push their way through like have you ever seen a documentary of the tube tunnels being dug? It's like that machine. It just drills through stuff. And they are kind of a pest to humans because we like to go on boats across the ocean, and when boats were made of wood, these things are a real problem, hence shipworm. But they do some very cool things. They're really neat. Some of them eat rocks. They're great.
They're absolutely amazing. I've learned all kinds of new things about bivalves from this talk, and I'm definitely a convert. We've had a question actually. I'll just drop in from Facebook. Darrett was asking. This is a lovely question, actually. How do they communicate with each other? Do they communicate? And would they feel lonely in their shells or by themselves?
It's a great question.
Yeah.
I don't know. We need a philosopher to answer whether or not they
Yeah.
feel lonely. Some bivalves live in large agglomerations, right? So there's always lots of them around. Most of them can't see and they can't hear, and I don't know if they really communicate with each other. Largely, the only real interaction they would have with each other probably is broad. So when they produce baby bivalves, a lot of the time it's by broadcast spawning, and you can trigger bivalves to spawn in captivity by adding the gametes of the opposite sex. So I guess that's a form of communication. You know when to release your gametes if you detect other gametes in the water, which is useful and good. Otherwise, all the effort would be for nothing. I don't know if they feel lonely. I don't think they're super social, to be honest with you. Sometimes some of the ones that bore into rocks also will just bore straight through each other. They don't care. They don't go round if they've both occupied one block of rock and one of them got their tunneled into a position and got himself sorted and was like, right, this is where I live now, and another one comes along afterwards. They will just plow through each other.
Wow.
I don't think they're that social, to be honest.
Yeah, not a lot of communication going on there.
No.
We've had another question from YouTube asking, can you explain about the periostracum? Because that's not a term that most of us are familiar with.
Right, so periostracum is the proteinaceous coating on sort of the outside of the shell that some bivalves have. And I mean, I don't know what aspect of it that you'd like explained, but broadly speaking, the amount of periostracum that any given bivalve has is variable. And some of them have lots of it, and it can be quite hairy. And that tends to be things that don't burrow a lot. So if they live on the seafloor or they're very shallow burrowers, they probably have more periostracum. So I'm thinking things like archoid bivalves, so arc shells often have a very shaggy, hairy periostracum. Razor mussels, actually solamiids, they're a really cool thing with their periostracum because they don't have the ability to, they use it as part of their sort of capturing. They have really long periostracum and they use it for that, which is quite neat. It's an organic proteinaceous layer of the shell. It's the outermost layer of the shell, really. That's kind of what periostracum is. Yeah.
Really good question. And one more question just quickly from Lynn, which we sort of touched on a little while ago. Lynn was asking how they procreate. So do they all spawn in that way by releasing their eggs into the ocean?
There's almost certainly some that do something else that I'm not aware of. There are a lot of bivalves, and some of them do very odd things in their personal lives. But the general, most of them are broadcast spawners. So they release gametes into the water column. Most mollusks are of some kind of hermaphrodite at some point in their lives, and bivalves are often sequential hermaphrodites. So they start out producing one kind of gamete and broadcasting that out, and then they change to they produce a different sort of gamete and they broadcast that one. But it's very variable. Bivalves do a lot of different things.
They really do. I think we tend to think of them as pretty sort of stationary and not very active, but they are doing all kinds of things, much more than we realize, right?
Yeah. They're busy little bees. They do a lot of stuff. Yeah.
So when they're feeding, do they clean the water? Do they improve water quality?
They can do. So because the ones that are filter feeding, literally, they just pump in water and push it out again when they're done. And when they pump it in, the particle matter that's in the water, microscopic dust and dirt and all kinds of nonsense, passes over their gills, and they can either sort it into particles I want to eat, in which case it goes through the digestive system and they use what they can, and the rest comes out in the way that waste products come out. And if they don't want to use it, they push it to the side of their mantle and it gets incorporated into little pellets called pseudofeces, and they just kind of dump those over the side. In both cases, the end result is to take the floating matter in the ocean and draw it down to the seafloor. So they clear the water that way by literally hoovering up all the particles and clumping them together into lumps that are too big to float again. So they clear water that way. Yeah.
That's fantastic. So nature's little water treatment plants, effectively.
They are little Brita filters of the sea.
Oh, I love that. And they often sort of kind of accumulate together, don't they? I don't know if this is the right term, but I've heard the term oyster reefs or mussel reefs. Are they habitat in the same way that other reefs are?
Yeah. So the technical term for an accumulation of bivalves in this way isn't reef, it's bioherm, believe it or not. But bivalves do also live on coral reefs. So reef is kind of a coral word. But bivalves, like the picture you can see here, there's a beautiful one of the tridacna clams is living alongside corals. Mm-hmm. But in the past, oyster beds, mussel beds both count as bioherms, and they produce a lot of habitat for other animals. Bivalves will sit on top of each other anyway, so dead shells provide habitat for more bivalves, but also little crustaceans, little fish, little seaweeds, little echinoderms, all kinds of things will live on these bioherms. And even before there were corals, bivalves were building hard substrate this way. So the other two pictures on this slide are some rudist bivalves, which are a really great group that are extinct now. But back in the past, they modified their body so that their one shell was like a big ice cream cone, you can see here. And then the other one was like a little lid just on top. And they agglomerated together and they made huge, huge bioherms that made a lot of hard ground for other things to live in. Those are, what you can't see there is the first picture, the one that looks like two pipes. So they don't have their lids anymore. They look hollow, but they only go down a certain way. Most of that massive shell is just calcium carbonate. It's just calcite. They're not hollow. They're very heavy. That's a very big bivalve.
See, looking at that, I would not have even said that was a bivalve, but we know how diverse they can be. They don't always look the same, do they?
No, they do all kinds of things, including looking like giant ice cream cones.
Absolutely. And they are, of course, super useful to us humans. They're very, very tasty, but useful in other ways as well.
Yep. So we do all kinds of things with them. We use them a lot for sort of adornment. So most people know about pearls and that pearls come from oysters. I hate to tell people this, but they don't come from the oysters you eat. You could eat hundreds and thousands of oysters every year and you will not find a pearl. I'm very sorry. Pearl oysters are a very different group of bivalve.
Good to know.
We also make buttons out of the pearly shell, the mother of pearl that's in the shell that makes the oyster. So some of the freshwater bivalves got used to make buttons, which was not very good for the bivalves, but you can still find those today in like museum collections. People have like shells with like the circle stamped out of them that someone made into a button. We also use them to make windows, believe it or not. So this is a related bivalve called Placuna placenta, and you can see its shell is translucent. So in the Philippines, they make windows out of them, and they make beautiful and very functional windows, as you can see. I think they're
they
gorgeous.
are stunning. Yeah,
Yeah.
absolutely.
And we can
Amazing.
also use a bivalve product called byssus to make silk. So many bivalves produce byssus. It's actually kind of a juvenile feature. Baby bivalves will stick themselves down with this protein thread called byssus. And most other bivalves, then they when they're not juveniles, they don't need it anymore, so they stop producing it. But some of them, including this thing called Pinna nobilis, produce masses of it. It's like a sand anchor. If you've ever been boating, it's like a sand anchor, and they use it to hold themselves still in the sediment. And humans have worked out that they can take these long protein filaments and they can spin them and weave them into this beautiful cloth of gold stuff called sea silk. And we've got a picture here of a glove made of it, which is really quite lovely.
These are fantastic. We've got some lovely sea silk gloves in our collection. That's just one example, and it's brilliant to think that they are made from mussel silk. Fantastic.
Yeah.
We've got lots more questions coming in, Katie. So I'll just pause briefly to take a few of our questions from our viewers. Great question from Verna, who says, "Hi, I work on pea crabs in the Dutch Natural History Museum, Naturalis." Hello.
Hi.
And they're wondering if the parasitic crustaceans inside of bivalves still get collected.
I mean, I assume people who study crustaceans collect them. If you're looking at modern bivalves, if someone is collecting bivalves from a museum, probably they would either take the pea crab that they found in it and give it to their colleague who studies crustacea, or they would release it into the ocean and be like, be free, find another bivalve to live in. I haven't heard of pea crabs being found fossil, but I do know that I know who I would ask. There's a guy at University of Florida, Roger Portell, who studies fossil crabs, and he would be the person I would ask about that. I don't know if we have any fossil pea crabs in bivalves. It seems likely, doesn't it? Crabs fossilize pretty well as well. I imagine that if you found really well-preserved fossil bivalves, you'd have a high chance of if you sieved the sediment inside them, of maybe finding bits of pea crab. That's a good question. I should look for those.
That's a great question. Yeah. We'll have a look. We'll do some research, see what we can find. And we've got a question. We've got a question from Facebook asking about scallops. They have lots of tiny eyes. Do they have good vision?
I think it's not bad. Their eyes are very different to ours, really, but I think they can certainly detect motion and light. They definitely they see you coming. If you're a scallop diver, they have a great response to seeing a predator, which is literally to leap into the water and clap their valves and swim away. So certainly their eyesight is good enough for that. Actually, a member of our museum staff, Suzanne Williams, she studies bivalve vision, or mollusk vision in general. She would know, but yeah, I think they're pretty good. They're not like a hawk or a human in terms of visual acuity, but they're certainly good enough to get away from a human, and they're fast.
Absolutely. Yeah, they are fast. I've seen some great footage of them swimming, and it always amazes me. The jet propulsion. Yeah. It's a good way to travel.
Literally, they just squirt their little siphons and away they go. Yeah.
We've got a few questions that have come in about extinct bivalves. So let's move on to talk about the fossil record, because bivalves have been doing all of this fantastic stuff for quite some time. When was it they first evolved, and how do we know?
So we know because we found them, which is kind of my favorite part about studying mollusks in general. Like, you know, they were there because they're there. Like, you go and see them in the field, you smack open a piece of rock, and you know how old the rock is, and you look at it and you're like, that's bivalve. I know it was there. So the earliest ones we have are about 520 million years ago. There's this beautiful little thing called Fordilla troyensis, and there are a couple other species of Fordilla, and there are also a couple of other genera. There are Tuarangia, which is found in New Zealand, where I'm from. And then there's also a thing called Purgitaia, which is also a little tiny thing. And we know they're bivalves as opposed to any of the other small mollusks that were around, because they have their little peg-like teeth that the valves articulate with. And they have the scars on the inside, like I showed earlier, with where the muscles and the soft parts attach, which are very characteristic in bivalves, and they're different to the ones you get in limpets or other small mollusks that you might think were roughly the same shape. And I mean, some of the mollusks that we have today still, like Modiolus, goes back nearly 400 million years, virtually unchanged in shell form. So we know that they were there because we see that they were there.
Yeah, absolutely.
Nice.
And what an innings as well. That is impressive.
That is unusual. Most of the living genera do not go back 400 million years.
Okay, good to know. Good to know. Yeah. They do fossilize really well, don't they? Why is that? What is it about their shells, I assume?
So it's because they have a shell. So most things with a good fossil record do it because they have good hard parts. And bivalve shells are made of calcium and, well, calcium carbonate, and they're nice and stable. So they preserve well in the fossil record. Yeah. That's pretty much what it boils down to. They've got good solid hard parts.
And quite beautifully, some of them as well. They look almost as good as the day they died.
Yeah, so the stripy one there in the bottom right is the holotype of Inoceremus pictus, and that is Jurassic. So that's 200 million years old.
That is amazing.
Really it's doing all right. It's still got the color patterns it had when it was alive, which I think is pretty impressive.
And over that long stretch of time, how have they evolved? Obviously, some of them seem to have changed very little. Is that the case for most of them?
Some of them have changed very little, but they have gone from a very minute thing that was either crawling or very shallowly burrowed to things that burrow meters deep into the sediment, to things that can swim, to things that eat copepods and catch them somehow. From being buried in the sediment, they catch these little things. Things that can that have photosymbiotic symbionts, things that have chemosymbiotic symbionts, things that build huge reefs. Bioherms, sorry. Like they do so many different things, and it all started from this little thing with no head and no brain. It was just crawling along the seafloor, 4 millimeters long.
They are amazing. And we've as I mentioned, we had a couple of questions relating to fossil bivalves. Russell on Facebook had asked what's considered to be the first bivalve, but would it be the little Fordilla?
It is Fordilla, yeah. So there have been putatively other early bivalves, but some of them have turned out to be squashed brachiopods, and some of them have turned out to be other things. Fordilla is the first one that we solidly know is absolutely bivalve. Yeah.
Brilliant. And Charles on Facebook was asking, what's the most amazing extinct bivalve and why, in your opinion?
Oh, God. The most amazing extinct bivalve. I mean, there's these things called the elatoconchids, which look like a snowboard. They're just this sort of, they're very, very long and very, very thin. They look like a duck's bill, and they might have been photosymbiotic, but we don't have any proof. It's just the shape that they are. We kind of go, what else could it have been doing? There's also inoceramids like Pictus, the one with the stripes we saw before. Those can be up to 2 meters long, but their shell is only about a centimeter thick. They're pretty amazing. I really like inoceramids. What else? There's just so many. That's a really hard question.
Too many. That's a great question.
That's a really good question. There's so many extinct bivalves.
Yeah, definitely. For a lot of the ocean fossils, we use them to tell us about the environment in the past. So can we do that with bivalves? Can they tell us about past environments?
Absolutely. They can do it in 2 different ways, which is also neat. So I said earlier about the elatoconchids that we think that they're doing something because of the shape that they are. Well, most bivalves, that carries really well. The shape that they are is that their shell is the only tool they have for interacting with the environment. So if you have an extinct bivalve, you can make a pretty good guess as to how it liked to live by comparing it to a living bivalve that's of a similar shape, because the laws of like hydrodynamics and how water and sediment interact have not changed. That's physics, right? That cannot change through time. So something like the scallop up the top there, top center, the very shiny disc-like one, that shape is a swimming shape. Those things are aerofoil shaped. This is a thing called a museum. is one of the best swimmers. They cannot burrow into rocks, and they cannot cement onto rocks. That shape is a swimming shape. So if you find a lot of bivalves with a certain range of shapes, you can make an inference about what the environment was like that they would have been there, if you see what I mean.
Absolutely.
Because they tend to live where they can function. The other thing that they can do to tell us about past environments is that the chemistry of their shells tells us about past environments, because they grow like trees. They start out small and they add layers. They add around the outside edge. So if you cut a bivalve in half, like I did here, you can look at the bands in it, and you can do chemistry on those bands. You can look at the oxygen isotopes, and you can reconstruct the past climate and on annual resolution for the years that bivalve lived. This bivalve is 50 million years old, and it still has the chemistry preserved in its shell that we can get summer and winter temperatures for 50 million years old for the sort of 25 odd years this animal lived. Yeah.
Wow. So indirectly by their shape and things like that, but also directly from the growth rings in the shell. Fantastic.
Yeah.
There is nothing these little animals can't do.
Oh, they're magical.
So they've been surviving for such a long time. A few people have been asking on Facebook and YouTube whether bivalves are affected by, for example, climate change. Are they facing any threats today?
Yeah. So climate change, just the temperature aspect, is a huge problem, because bivalves are very fussy about their temperatures, to be honest with you. Some species live over a vast area, but when you look at the area that they live, the temperature envelopes that's experienced in that area is very narrow. So they're quite fussy because they can't move, right? Other animals will pick up and move if the environment changes and they don't like it anymore. If summers start getting too hot, they'll go. Bivalves are not capable of doing that. Even the ones that can swim can only swim for a few meters. They're not migrating. They stay in the same kind of area. So yeah, the climate changing is quite bad for bivalves, which is not great for humans who like to eat bivalves, which is a lot of us. Like they're a serious food source. So yeah.
Yeah. Linked to climate change is not just temperature change. There's also ocean acidification, the ocean getting more acidic. Will that impact bivalves as well, forming their shells?
It will. They have a little bit more flexibility with that, but it's going to catch them eventually. So their shell also has proteinaceous layers in it, and some of them have more protein than others, and may react better to ocean acidification. But yeah, like in the Arctic, you can see changing amounts of shell wear, because they can repair their shells while they're alive, but that takes energy, right? So if they're not getting enough food, then it's all feedback, it's not great. I mean, the temperature will probably get them first, but the ocean acidification is not good.
Yeah, that's not brilliant. And ocean plastics, is that an issue for bivalves?
Yeah, so plastics don't break down, famously, but what they do is break up. They break into tiny pieces, and when they're the appropriate size, bivalves will filter them, because they filter everything. They ain't picky about that. And if it was just inert plastic, that wouldn't be a problem. They just take it in, they go, oh, this isn't food, I don't want to eat this. They bind it all together into some pseudo-feces and they dump it, and then it would get buried. And that kind of minimizes the problem. It's no longer in the water column for other more sensitive animals to eat. But a lot of plastics, when they break up, they leach chemicals, and those chemicals can be very, very bad for bivalves and for other animals. So bivalves can take on toxins and just dump them into their flesh and into their shells if they're not immediately killing them. But then something else will come along and eat that bivalve, and it's bioaccumulated all of this poison, and so the poison goes up the food chain, and it's not good. It's not good at all.
Yeah, it concentrates up the food chain, isn't it? So yeah, not ideal. But climate change, plastics, is it all things that we can do something about if we choose to? We've got lots more questions coming in from our viewers.
Cool.
So I'll just get on to a few more. I know you love them.
I do.
We had a great question coming in that came in a little bit earlier when we were talking about their growth ring. Somebody asked on YouTube, how long do they live and how do we measure how old they are? Do we count the rings, or is it a bit more complex?
So, I mean, it can't. Everything is always a little bit more complex once you start. But as a broad answer, we know how old they are because we can count the bands in their shell. The bands come in dark light couplets for chemistry reasons I won't get into. So you know when you have annual banding in your shell, and you can just count them and you know. The oldest bivalve I know about was recently dated as having lived to over 500 years when it was finally dispatched. Yeah, Ming. It was a member of a species called Arctica icelandica, which lives in the high latitudes. And I mean, people eat them, which is, it takes them so long to grow to an edible size, and then people eat them, and you just sit there going,
oh.
Stop. But some of them have a really short lifespan. Some of them build their shells so fast you'd be amazed. You'd think you could hear them growing. Like, there are bivalves with a lifespan of like months. Even your standard giant clam lives a long time, but it doesn't live 500 years. Arctica icelandica only get this big. The bands are very thin. They're big, but they're not giant clam big. So a giant clam puts down shell much faster than Arctica.
Yeah, really impressive. We've got a few more questions. So Andrew on Facebook was asking about their evolution. He was asking whether there was a great shift at any point in which mollusks were dominant on the Earth during one of the mass extinction events. Did that ever happen?
I don't think they've ever been. I mean, what does dominant mean? They've been the majority filter feeding large calcareous organism. They sort of took that mantle over from the brachiopods into the Mesozoic, but because they're not sort of top of the food chain, so it's difficult to say that they were dominant. And I don't believe there's ever been a time where they were like, most of the biomass on Earth was bivalve. Like, I don't think that's true. They're very good at surviving mass extinction events, is the cool thing about them. So the Permo-Triassic extinction and the Cretaceous-Tertiary extinction, two huge extinction events, they went through both of those. And in terms of different bivalves of functional groups, so different ways of making a living, almost every single functional group bivalves have ever had has made it through. And in terms of like taxonomic families of bivalves, almost all of the ones that we have today made it through the Cretaceous-Tertiary extinction.
Yeah. So they are the great survivors.
They are good survivors. They do. They hunker down and they make it through.
Yeah. We had a question a little earlier on YouTube asking whether we have any of these huge specimens like our giant clams. Are they on display anywhere in the museum where we can go and look at them, or is it just on the shelf
No, there's a good one. There is a good one in, I think it's the Treasures Gallery. So if you go in through the like by the BGS shop, there's that lovely gallery with the dark navy walls, and it's got lots of beautiful things on plinths. One of the things on plinths is a very nice giant clam. So yeah, you can see one of those in the museum.
Absolutely, and well worth seeing. They are pretty fantastic.
Yeah.
And one more quick question from Noah, age 6. So Noah, I think, is one of our regular viewers. He's asking, what is the most unusual bivalve that you have found, you yourself?
Me personally, the most unusual bivalve I've ever found. Ooh, that's a hard question. I think. So I don't know. I don't know, Noah. I'm really sorry. There's so many of them, and they do so many different things. Oh God, I think probably. I honestly, I'm just. Oh, you know what? Do you know what a gooey duck is? So there's this thing called a gooey duck, or panopia, which is a bivalve that can dig 2 meters almost down into the sediment, and they don't all fit inside their shell. So their siphons make this long, it looks like an elephant's trunk, and just the tip of it pokes out of the seabed, and that's how they get their water in and out. And they look like a long elephant's trunk with just a bivalve shell at one end. I found those fossils. Those are really cool.
Yeah, that's a good example. That's a really good example. And Lynn on Facebook was asking, but do you eat any of bivalve mollusks?
I do eat bivalves. Yeah. I like scallops and I like mussels. I'm not big on oysters. I don't like the texture, but Yeah.
I love mussels and scallops, definitely. It hasn't put us off eating them, knowing about them.
No. No.
No, Katie, we are almost out of time, unfortunately. But just before we do wrap up, bivalves, they have this incredible past, but they could be really, really important for our future, right?
Yeah, so the kind of cool thing about bivalves and people is that bivalves are a great source of protein for humans, and we need protein to live. And they're one of the few kinds of animals where if you basically farm them, so aquaculture, instead of most of the time when you farm an animal, you have to come up with ways to deal with its effluent, basically the stuff, its waste products, and they can be a big problem, and they can put a lot of nitrates into the ocean and the soil, and that's quite bad. Bivalves, like we've been talking about, clean water. The sustainability of bivalve aquaculture and the things that it can bring to the environment are really quite positive. So yeah, I think bivalves are potentially one of the things that we should be partnering with as the way forward into a slightly more sustainable future, I hope.
Absolutely. Good for us and good for the bivalves as well. A sustainable food source.
And good for everything that likes to live amongst the bivalves as well. So if you're culturing oysters or you're culturing mussels, you can also be providing habitat for a biodiverse kind of an area if you do it in a certain way. So I think that's pretty useful as well.
Oh, that is brilliant, and a lovely positive note to end on, I think, which is it's been a fantastic talk today, Katie. I've absolutely loved finding out about bivalves today. We've got our beautiful 3D rendering here. Is this from our collection?
No, no, this is one that I micro CT scanned a few years ago, but I put this one here because this is one of the great survivors. So the group of bivalves that was the most common when the dinosaurs were alive, this is the living species that we still have off the coast of Australia. This is the one that jumped out of the boat. This is the species that jumped out of the boat. Yeah, so this is one bivalve positivity. You can get through anything.
Absolutely.
If Trigonia can.
Yeah, exactly. Forget lockdown.
Exactly.
Be more scallop.
Exactly.
Oh, brilliant. Well, sadly, we are completely out of time. Katie, thank you so much for joining us today. I've had a brilliant time. I've realised I unconsciously came dressed as a disco clam today. That's how much of a live-out convert I am. So thank you very much for introducing me to this brilliant group of animals. And hopefully we can have you on again, because I know we've barely scratched the surface. There's so much more to talk about, isn't there?
Oh, absolutely. 500 million years worth of history. But yeah, Definitely. Thank you for having me. It's been fun.
Thank you so much, Katie. We'll say goodbye to you for now. And thank you to you, our viewers, for joining us today. I hope that you enjoyed that as much as I did. Thank you so much for all of your brilliant questions as well, including some of the ones that really foxed Katie. That's fantastic. Do join us again. We are here every Tuesday at 12, every Friday at 10:30. This coming Friday, we've got a fantastic talk with a wildlife photographer coming up. So do join us. Keep an eye on our social media feed and also on our website to find out what's coming up. But for now, we will say goodbye. We hope to see you again next time.